Thank you very much, Shihab. Thank you for the invitation to give a presentation. It's a pleasure to be here. Indeed, my talk will be on the application of machine learning to enhance algorithms in computational finance. And it's work from a little while ago, like 3 years ago. I think, especially for such an online setting, it's maybe a presentation that is relatively easy possible to digest. So that's maybe a good reason to have this presentation among others. So the agenda for today's talk is I'll first say something basic on financial derivatives pricing, talking about the Feynman-Cutch relations. I'll do a very brief introduction into machine learning and the use of neural networks. And the main part of the talk is about parameter calibration. How can we use machine learning to do parameter calibration? Maybe it's best to have the questions afterwards, either in the chat or just by speaking. But maybe it's a little difficult to have questions in between. And this is joint work with the former PhD student, Dr. Swai-Cheng Liu, and Professor Sander Boté from the CWI, who is an expert in machine learning, and a former postdoc, Anastasia Borovic, who is now assistant professor or a lecturer in Imperial College London. Well, this is the standard setup. Hey? I wanted to introduce some notation and explain the things we're doing. And I do that on the hand of the Feynman-Cutch theorem. If we have a linear partial differential equation, like we see here, dv dt plus some operator times v is plus g, a source term, is equal to 0. And the operator is a convection diffusion operator, mu dv dx plus 1/2 sigma square, the second derivative of v with respect to x, and it comes with a final condition, a condition at final time capital T. Then we know that the solution can be found by means of the Feynman-Cutch theorem, and the solution can then be written as can be derived as the expected value of the integral from little t to capital T of g that depends on s and xs ds, the g that we also see here as the source term, plus the final condition, the expected value of this expression, that is the solution of the PDE. And xs, that's a stochastic process. It's governed by the Ito differential, the Ito process, whose dynamics are as follows. dx is mu ds plus sigma d omega, where omega is here the Wiener process, d omega, the Wiener increment, and x sub t is little x. So that is the basic building block, and whereas sometimes people solve the PDE with finite differences, finite elements, we typically go via the Feynman-Cutch theorem, and we typically start to approximate these expectations. Another connection in this way is the connection between, in optimal control, the connection between the Hamilton-Jacobi-Bellman nonlinear partial differential equation and the concept of dynamic programming. If we have a model Hamilton-Jacobi-Bellman equation, dv dt, plus, say, the supremum of A in a set capital A, where A determines the drift term, the convection term, and also the diffusion term possibly. So mu dv dx plus 1/2 the trace of the second derivative times sigma transpose, and they all depend on that parameter A, plus g depending on t, x, and a is equal to 0. That's our Hamilton-Jacobi-Bellman equation with a final condition again. Then associated to this, the solution can be found by means of dynamic programming, solving a stochastic control problem with the following value function. V, depending on t and x, is equal to the supremum over the supremum of alpha. So we We have a slightly reformulated problem. So A and alpha are related. Of the conditional expectation, given a filtration at time t, that's what we denote by this, this expectation symbol with a sub and a superscript. The integral from little t to big T, G, depending on S, stochastic process, X, depending on alpha and control alpha, ds, plus the final condition, H, which depends on X at final time capital T. And again, X is a stochastic process, which is governed by the controlled forward stochastic differential equation as follows. dx is mu ds plus sigma d omega, and mu and sigma depend on alpha and on the controlled process itself. So again, we have a connection between the PDE and the solution by means of a stochastic formulation. And again, we would go via the stochastic formulation for the solution. A final connection here is a semilinear PDE and the so-called backward stochastic differential equations. So if we have a semilinear PDE, dv dt plus the operator from before, the linear operator from before times v, plus a function g, which now depends on v itself and on the first derivative, equal to 0 with a final condition, then this PDE we can also solve in a stochastic formulation by means of first having a forward stochastic differential equation for x. dx is mu ds plus sigma d omega. X at time little t is equal to little x. And it's followed by a so-called backward stochastic differential equation. So the solution can be found by first processing a forward stochastic differential equation. From the forward stochastic differential equation, we get a final condition for y. Y at final time capital T is then h, which depends on capital X. And then we have a stochastic differential equation which goes backwards in time. dy is minus g ds plus z d omega. And this is a stochastic differential equation which proceeds backward in time. And there is a well-known theorem that says if we do this procedure, then y at little t is the solution to the partial differential equation, and z at little t, we see the z appearing in the b as the e here, z at little t is a scaled version of the first derivative of v. And again, this is the way we proceed typically. Why do we proceed with these expectations? Well, of course, this is an integral formulation, and it does not is not hampered by the curse of dimensionality. In principle, with this expectation formulation, because here also with the forward-backward stochastic differential equation problem, we end up with expectations, conditional expectations. With these, we are not hampered by the curse of dimensionality, and we can go to high-dimensional problems. All right. Now we want to solve some of these with supervised learning using neural networks. So first, say a little bit about this methodology. So if we want to approximate some function f from space x to y, x is in Rd and y is in R. We have a scalar output in this case, and we're going to use a neural network that we denote by phi. A neural network mapping from x to y with parameters theta, and the thetas are the parameters of the neural networks, the so-called weights and biases that need to be set by means of training before we can do a testing phase. Supervised learning is essentially learning with data, as you know, and then for example m pairs, x y y y, m pairs, x from space x and y from y, y being the labels, and we know that f xy xi is equal to yi. Then supervised learning means that we want to mimic, we want the neural network phi, capital Phi, to resemble F as closely as possible. And we do that by minimizing a loss function. We try to minimize the distance between the labels, y sub I, and the neural network output, phi. And we do that here with the mean square error in some appropriate norm. And we have some work in that direction. So the work that I'll present today is are essentially the first two papers here. The first two papers, they are part of the presentation here. And we also have a Monte Carlo scheme in which we learn how to take big time steps. That is the 7-week scheme. Yeah, and then we also have unsupervised learning and reinforcement learning. In that case, data is not labeled. So that means that learning should be self-organized. And we cannot compare the neural network output with a label because we have no labels. It's more difficult to set up an algorithm. It requires more knowledge of the underlying PDE or the underlying structure we're dealing with. And in reinforcement learning, we deal with an algorithm that reacts on its environment. So essentially, you can think of an agent with a set of possible actions, and a trial and error strategy is followed where good steps are rewarded and bad steps or unpleasant steps are penalized. And this way, the neural network learns what is good behavior, or what is required, and what is especially not so pleasant. And so if we don't have labels, we cannot compare the neural network output with a label. So we need to come up with a loss function such that when it's minimized, we still have that the neural network output resembles that function f that we're looking for. So essentially, we employ structures of properties of f. Like if there's a PDE involved or a physical law, the physical law is incorporated in the loss function. So a physical system describes f, or properties of a physical system are included in the loss function. Or in our case, properties from a financial market. Or, for example, properties of a probability density function, the fact that the integral of a probability density function should equal 1, for example. Those are, or that we cannot have negative values there. These are properties that we can also include in such a loss function. And we also have papers in that direction, more recent papers. In finance, we do a lot of regression, and we learn regression in papers that have appeared in Applied Mathematics and Computation with Christopher Anderson, PhD student. And again, we look for large portfolios of financial derivatives or high dimensional problems in which we need to do regression. And next to deep learning for regression, which is a way of supervised learning, we also need to learn there about early exercise regions, and whether or not a point is in the early exercise region. That is more or less reinforcement learning, if you wish. That is some form of reinforcement learning. We also have unsupervised learning. We have a paper in the Journal of Computational and Applied Mathematics on physics-informed neural networks, where we look for the weights between the optimal weighting of boundary loss functions and interior loss functions in PDE solutions. And we also look at stochastic control, dynamic programming approaches, and in particular for forward-backward SDEs. And that is also some form of reinforcement learning. Now, if we return to the Feynman-Katch, of course, in the financial setting, we deal with the Black-Scholes equation, for example. Here, the PDE is the Black-Scholes PDE with a final condition, the option payoff. We look for the price of an option of a European option. And again, then the value of the option is the unique solution of the discounted expected payoff, the discounted expected final condition of the option under a risk-neutral measure, which is denoted by Q. Given that we have all the knowledge up until time little t for our process. And in the financial context, then the stock S, capital S is the stock, little v is the option. Then the stock S is prescribed by geometric Brownian motion. ds is rs dt plus sigma s d omega under the risk neutral measure. The important thing here is that we won't look too much into the Black-Scholes equation, but similar relations also hold true for other PDEs that are more often used in finance. For example, PDEs that are found when we deal with stochastic differential equations under stochastic volatility, for example. And that's in the next slide. So there are different models for option pricing. These are the stock price models. The first one is the well-known geometric Brownian motion leading to the Black-Scholes equation. But more realistically is the so-called Heston model. It's a stochastic volatility model. It comes with a similar sort of equation for the stock. ds is rs dt plus a sigma and volatility, the square root of the variance times s d omega. But now we call it stochastic volatility because there's a second SDE, an SDE for the variance. D omega is kappa nu bar minus nu dt plus gamma, the square root of nu d omega. And this is the variance. Kappa is the speed of mean reversion. V bar is the mean value of the variance. Gamma is the volatility of the volatility. And there's also a correlation between the Brownian motion for the stock price and the Brownian motion for the volatility. And this correlation should typically be negative, right? When stock prices go down, the uncertainty or the volatility, the variance goes up. So this is typically a negative number. Now you see many more parameters appearing here, and these parameters need to be tuned to the market. We have R, interest rate. We see kappa, the speed of mean reversion of the variance process. Nu bar is a parameter. Gamma is a parameter. Nu zero, the initial variance, is a parameter. And rho, the correlation, is a parameter. Moreover, if we make it even more realistic, unfortunately, we have more parameters. If we have a model with stochastic volatility and jumps, then we see here a Poisson process XP appearing, jumps in the stock price model. Stocks also jump, especially on the short term. And then next to the first part and the second part, we also see a jump part appearing, and with even more parameters. So whereas we have 5 parameters to calibrate to the market when we deal with the Heston model, we will have 8 parameters, 3 additional parameters when we are dealing with stochastic volatility and jumps, because there is the intensity of the jumps, the average jump size, and the variance of the jump sizes. They come as extra parameters. So the exercise of calibrating such a model to the market is essentially the exercise in this case of tuning the option or steering the model towards the option values that we observe. And I'll show that in a minute. So here's the summary of that exercise. We have again connected to these stochastic differential equations in this same way. Here is a partial differential equation. The Heston option pricing partial differential equation looks like this. It's a two-dimensional, essentially 2 dimensions plus time, dv dt, plus dds terms, like the derivative with respect to the stock price, and dd nu terms, derivatives with respect to the variance, and a mixed term. And here you see also these parameters appearing: kappa, nu bar, rho, v0 is there. So calibrating means fitting 5 parameters, namely the correlation coefficient rho, the long-term variance nu bar, the reversion speed kappa, the volatility of volatility gamma, and the initial variance nu zero. We need to fit them given market option prices, the calls from the market, VC, and the puts from the market. That is the exercise that we need to do. So we need to solve, essentially, we need to solve this problem. We need to find the parameters, but essentially we have the option values. The option values are from the market. And we have specifically the final condition. The payoff at final time for a call is the maximum of S at final time, capital T, minus K and 0, which we denote by this superscript plus. And for the put option at final time is the maximum of K minus S at capital T and 0, where K is the strike price of the option. Now, this is the exercise, but typically in practice, we don't look so much at option values, but we look at implied volatilities. The volatility that the market thinks, the volatility for which the market thinks the future uncertainty behaves. Yeah? Implied volatility is a strange measure, if you wish. Essentially, a famous quant, Ricardo Rebonato, once said, it's the wrong number in the wrong formula to get the right price. So it is a number. The wrong formula is the Black-Scholes formula. We put a number in the formula to get the market option price. The right price is, the market is always right. So the right price is the market option price. But we use the formula that we shouldn't really use, namely the Black-Scholes formula, and we put in a number in order to get to our market price. Why are people in practice doing this? Well, it is a very handy measure to see how expensive, relatively expensive, an option is. Depending on the shape of such an implied volatility curve, we can see how the market, market players expect the market to behave. And relatively speaking, we can see that a high volatility, a high implied volatility means relatively expensive option prices. So for a trader, the implied volatility surface, a surface that can be time dependent and strike dependent, K dependent. For each different option, we have a different strike price and we have maybe a different time. And therefore, we have a whole surface of volatilities, sigma implied, depending on time and on strike. So mathematically, we have that an option value is found by means of, say, a Black-Scholes formula, which depends on asset price parameters sigma and R, and option value parameters capital T, K, and also on S0. And this Black-Scholes formula is monotonically increasing in sigma. Higher volatility means higher prices. Now, essentially, we are looking for the sigma for which we get the market price back. So we are looking for the implied volatility. We call that the implied volatility, which gives this inverse function where we include the market value and all these other parameters, the sigma, which then gives back the market price from the Black-Scholes formula. All right, how do we typically find the implied volatility? Well, this is, of course, a course in computational finance. We typically use a root finding technique. It's an implied formula we look for the formula, we look for a parameter in the formula, and we use a root finding technique. Just nonlinear iteration, and we can think of Newton-Raphson or the Brent iteration. There are many options, the bisection technique, etc. And especially when I say this, I'm thinking of in a machine learning context. We want to do this many times in a machine learning context, and we can have all sorts of input parameters. It should always work. So this root finder that we will be using in order to train our neural network, that should be a very robust procedure. Newton-Raphson, we all know, it only converges when we are in the ball of attraction. Bisection is very robust, but it's very slow. And Brent is some sort of in between. It converges rapidly if it's possible to converge rapidly, and otherwise it falls back to an interpolation scheme which is specifically robust. So what do we do if we want to price options, for example? So with the neural network, we will come up with the calibration neural network, and it consists of two stages, a forward pass and a backward pass. And for now, I will talk first about the forward path. The forward path is solving the equations with the help of neural networks and supervised learning. So essentially, what we typically do before what we typically did before we had any machine learning technology, we have a ground truth. We have our parameters as input. Then we had our Heston model. In order to have fast computations, we used the so-called cost method based on Fourier cosine expansions. That gave us an option price, a European option price. And then we used the Brent linearization in order to extract the implied volatility. So the first step in our procedure towards artificial neural networks that we abbreviate with ANN is we have these parameters. So this is the forward model. We learn the solution. Of the procedure. And in a first intermediate stage, we would have two neural networks. We would learn, first is the Heston artificial neural network. We would have option prices as the labels, and we would have a neural network learning how to get from input parameters to the output option prices. And then we would have a second neural network, the implied volatility artificial neural network, that learns how to get from an option price to an implied volatility. But of course, that was an intermediate step. In a way, we can directly go from the parameters that we have directly to the implied volatility. And we glue these two neural networks together in one neural network, the Heston implied volatility neural network, and we can directly go from the parameters to the implied volatility surface. It's supervised learning. It's rather classical. But let me explain a little bit what we do. We generate data points of input parameters, rows and new zeros and gamma and all these parameters. We generate sample data. We calculate the output, the option price and or the implied volatility, and we can use the cost method, but we can also use, because it's very efficient, but we can also use a PDE method or Monte Carlo to form a set of in and outputs. So the outputs are first made by a classical technique. Then we split the above data in the training and the test part. We train the artificial neural network on the training data set. And then we evaluate the artificial neural network on the test data set. And when these mean square errors are in the same ball game, then we know there's no overfitting taking place and it's going well. And we do an exhaustive testing. If all goes well, we can replace the original solver by the trained artificial neural network. And the reason is that that is much faster, especially if you calibrate. You want to do it fast because you don't want the market to run away before you have even calibrated your model. However,
sorry, one question.
Yes, let me see. Yes.
I had a question just to understand from a practical point of view with traditional methods, how much time does it take to use?
Yes. So say you have like 5 parameters to tune, and you have a number of option prices. It may well be that you need like 10,000 iterations in order to get to a good quality output. 10,000 iterations. They may, in this case with the cost method, in the hypothetical case that everything is perfect, they may take less than a second. But 10,000 times less than a second is still a rather large amount of time. So it could take a minute, but a minute for just one test can be a lot. So, or say 10 minutes maybe, and that's too much, right? So an iteration to fit parameters. Each time you iterate, you need to solve the PDE. You need to solve the PDE. We do it highly efficiently in this model situation with the cost method. And the cost method only takes 0.1 second approximately, but again, 10,000 times 0.1 second is still 1,000 seconds, and 1,000 seconds is still like 20 minutes. So that is still expensive. All right.
Perfect. Thank you so much. Cheers.
Okay. I wanted to say something about approximating a steep gradient, because we often encounter steep gradients in finance, and they are not so easy to deal with neural networks. And as a toy example, let's look at the tangents, just the tangents between 0 and pi over 2. So between x being between 0 and 1.55. And we know that the gradient grows exponentially when x approaches the upper bound, right? We all know that that it goes like this. The derivative is 1 over cos square, and that goes to infinity quite rapidly. Now let's look what a neural network does with this. How can this approximate? What should we choose? So let's take 5,000 equally distributed data points in the interval. Let's choose randomly 90% as the training data and 10% as the test set. And the first observation was when we vary the number of nodes while keeping 2 hidden layers, we have a very slow reduction of the error. So let's vary the number of layers, for example. So and do something else. A first alternative test is we vary the number of layers, of hidden layers in the neural network. We keep the total number of nodes fixed and train the artificial neural network. And that brings us this. Again, a slow convergence. If we have 2 layers, 3 layers, 4 layers, we keep the total number of nodes fixed, but we increase them in this table, and we see that the error is 2 with 2 layers, and it hardly reduces with more nodes. We see that the error is, well, it's a little smaller with 4 layers, but still, you know, the error decay is not that impressive. It even increases here. As an alternative, and this is due to the very steep gradient. The artificial neural networks have difficulty approximating high gradient functions accurately. As an alternative, we first do a transformation, and we call that a gradient squashing technique. We do a transformation, we do a log transformation. We say x bar is the log of pi over 2 minus x. And if we do that, and we evaluate our tangents, and afterwards we transform back, then with only 2 layers and the log transform, we see a drastic reduction of the error. So we see we win at least 1 order, and the convergence just continues, and the approximation is in highly satisfactory regions. And the reason being, of course, that with a log transform, and so the artificial neural networks are known to converge slowly when approximating functions with steep gradients. But after a transformation, then we essentially work on this function. Y is the tangents of pi over 2 minus e to the x bar. And then the gradient looks like this. And this gradient is much less steep and therefore much better to approximate than the original function. And after a back transformation, we have this, as you see, we have this very highly satisfactory approximation accuracy. And the reason that I show this is that we also encounter such relations, steep gradients, if we think of the function, the implied volatility relation to the option value. Also there's a very steep gradient function involved. And many people and many master students do such an exercise, and they simply can't get good accuracy. And the reason being that, well, this steep gradient is not easily handled. So we also do, in our setup, we do also a gradient squashing technique to deal with the gradient in the volatilities versus the option prices. Well, the first thing we do is we look at time value. We subtract the intrinsic value in order to scale to some extent. But the important step to get some accuracy is that we look at the log of the option value divided by strike price K. And if we work in this setup, and we have as input, we have the parameters that we are dealing with, and as output, we have the implied volatility. If we work with the original option value V, then our mean square error is only 10 to the power minus 4, and our absolute error is 10 to the power minus 2. But if we work with the log price instead, if we do that gradient squashing technique, then we win drastically in the accuracy of the neural network. We achieve accuracy like 10 to the power minus 8, and in mean absolute error 10 to the power minus 5. So sometimes it's better to think a bit about what function are you approximating, rather than having more layers, more nodes, and try to have this as a working horse. Steep gradients are just very, very difficult to approximate. And in finance, also when we're dealing with probability density functions, we often encounter functions with steep gradients. Well, the next step is we do that implied volatility computation. We do that Brent iteration or bisection or Newton-Raphson. And there the question is, does it pay off to go to a neural network? So here is a small example. We compute the implied volatility with a neural network. So essentially, we learn the 1D inversion of Black-Scholes. We do learn the 1D inversion of Black-Scholes. We do 20,000 different cases, 20,000 runs, and we compare CPU and GPU computation. And we look at robustness, because we want robustness, because in neural network training, you get all sorts of combinations of parameters, and it should essentially always work. Not a number is not an option. If we do 20,000 different cases and we would do Newton-Raphson, GPU takes 19 seconds, CPU 23 seconds, so there's not much of a speed up. And we know it's not robust because we need to start in the ball of attraction. If we do bisection, we have essentially many more, we have much more computational time, a factor of 15 on the CPU, even more so, but we know that it's robust. Okay? And if we do 20,000 Brent iterations, it's like 52 seconds on the GPU, it's like 60 seconds on the CPU, and we know that it's robust. However, in comparison, if we have trained a neural network, and we don't talk about the training time, it's once, it's offline, but if we have a trained neural network and we let it run these 20,000 cases on a GPU, it's like 0.2 seconds, and on a CPU, it's approximately 2 seconds. So, and it's robust. So this is one one good example for where a simple exercise, it's a very simple exercise, can still give you a drastic speed up in the case of neural network technology.
Can I ask you one question?
Yes, sure.
If this is a 1D inversion, how would that compare with just taking an interpolant on the inverted values of the sigma of the implied volatility, for example, instead of doing a neural
First of all, it's 20,000 cases, right? So 20,000 cases. The Brent methodology is based on an interpolation, right? The fallback option in Brent is this interpolation. So of course, implicitly, this is also included in an implied volatility artificial neural network, because a neural network is also a way, some sort of interpolation. The point is more that we have a technology that's extremely fast to evaluate, and it's even also parallelizable. So I would say, I would guess that such an interpolation is similar to Brent, to doing Brent for 20,000 different cases, something like this.
Thank you.
All right. Okay, now we go to that calibration. Essentially, you can say we learned the forward model with supervised learning. We had a proven technology, numerical analysis technology, by which we trained the neural network. We replaced that technology by the neural network, and we have our forward model, which is fast and efficient. And then what we essentially do when we do calibration is we look at the difference between a model value and a market value. And that can be an option value or an implied volatility. In our case, it's an implied volatility. And we have a functional, capital J. It's a sum over n implied volatilities. They depend on the parameters, on some parameters. They depend on moneyness and a scaled time. There's a weighting involved. Sometimes there's a weighting involved. In our case, the weights are all 1. And there's a regularization involved, like a regularization that these theta, these values that we are looking for, they should not explode. In finance, we work with moneyness, S over K, and we work with time to maturity, tau being capital T minus small t. N is the number of samples, and lambda bar is a regularization function. And what we do during calibration is we want to minimize for the parameters that we want to deal with in Hest, and this is rho, kappa, gamma, nu bar, and nu zero. In Bates, the model with the jumps, it is these 5 plus lambda j, the intensity parameter, mu j, the expected size of a jump, and sigma j, the expected variance of a jump. And for Black-Scholes, it would only be sigma. And so the objective is we want to minimize this functional over the space of our parameters to calibrate. Unfortunately, it's not so easy. First of all, it's computationally intensive. And moreover, the objective function is often non-convex and non-linear, especially for high-dimensional model calibration. And so if we look at a surface, here we look at a surface where we have the speed of mean reversion, kappa, in the Heston model, and we plot it against the volatility of volatility, gamma. And we see essentially that there are multiple optima. We have this strange V-shaped thing, and there are multiple optima. Essentially, we know that a large speed of mean reversion and a small volatility of volatility essentially gives the same option values as a large volatility of volatility and a small speed of mean reversion. So there are multiple optima. It's a not well-posed problem, if you wish. So if we want a fast and generic calibration framework, we should have at least 3 components. An efficient solver, well, that's what we have with this artificial neural network. A global optimization, well, that is typically slow to convert, so we need to be careful with that. And a parallel computing environment, right? And this is what we do when we calibrate the neural networks. So this is the essence of our CAN. So the first thing is well, we have that training and this prediction phase. We want to have the artificial neural networks learn what numerical solvers do. So the first phase is we have that forward phase. We have the forward phase. We want to learn from input to output. The second phase is the backward phase. We want to go from output. We are given market option values. What are the good parameters? And we do that as follows. We do that with a framework, the CAN framework. It consists of 3 phases. The 3 phases are, however, intertwined. We have one neural network, and this is the forward phase. This is the learning phase that we just saw. The black circles are the things that we know. This is supervised learning. We have the input parameters. They are on the left-hand side at the input layer. We have the hidden layers that we need to learn. So they are open circles. And we have the output layer. We know the solution. That's, again, a closed one. In the learning stage, we go from left to right. We go from input to output. We learn these layers. And that's the forward problem. That's the training phase. It's offline. Now, the next phase is the calibration phase. Essentially, we keep our neural network technology. We keep exactly the same technology. But these open circles in the forward phase, they have now been learned. We have learned how to get from input to output. We fix those now. We don't change them anymore. After the training phase, these are fixed. The weights and biases in these hidden layers are fixed. And we know a market option value. And then the task is, what are the suitable input weights and biases? What are the suitable input parameters in order to get this established? So in the calibration phase, we fix other parameters of the same network. These are fixed, and we release the input layer. We ask ourselves, what are suitable input parameters? Yeah. And that is the backward phase or the calibration phase. So again, summarizing, we have a forward path where what we just explained, we have all these parameters. We have the Heston CAN, and we get the input. And we fix the hidden parameters of this in this forward phase. Then we have a backward phase. We have the implied volatility from the market or the option values from the market. And we know, of course, some option parameters, the time to maturity, this initial stock value, the interest rate we know, K we know, the strike price. And then we do it in backward, and we ask ourselves, what are the initial nodes? What are the nodes in the what are the weights and biases of the neurons in the input layer? What are, in other words, what are the rho, kappa, nu zero, nu bar, and gamma that belong to that output? And for that last phase, we need a global optimization method, because in that last phase, we encounter those multiple optima. And then we would say, isn't this very expensive? But if you look at it, we only optimize these weights and biases of a limited number of nodes now. It's only 5 nodes if we have 5 inputs, or 8 nodes if we have 8 inputs. And then it's still affordable. Especially we use a parallel version, and we use differential evolution, which is a global optimizer. We only use it for the backward path, and only for these 5 nodes that need to be optimized in that setup. And by doing that, by combining it this way, we have a robust version, and it is rather efficient. So we have the forward path, it's offline, we train it, and the backward path could be online. And that also may require some time. It requires some optimization. So it still requires some time, but we can do that in parallel. So let me show some results. We have we define a training set. So we have different parameters. For all these parameters, we have ranges, value ranges. We learn, the neural network learns to be in this range. For example, the volatility of volatility is trained from 0.01 to 0.8, and it's trained with Latin hypercube sampling. And all these parameters, they are trained in a certain range. And in that range, we make sure that the neural network performs satisfactorily. Yeah? And we train with the forward process. We get European option prices with the cost method. We have put prices, and then we do the put call parity to also get call prices. And for the implied volatility, we learn it with the Brent linearization. If we do that, we, as you've seen before, we get an error of 10 minus 8, something like that, during training, for training, and also for testing, for the testing in order to check for overfitting. We see that we are in the same ball game, 1 10 minus 7 or 8 10 minus 8. It's not too far apart. So we are essentially happy with the forward path. And then we look at the backward path. The backward path is, we do here, here we say, let's take some strikes, let's take some K values, some capital T values, 35 samples, and let's train these parameters. We insert the parameters, and we see if we can find them back by the calibration exercise. And if we do that, we still need to. So we check the performance over like 15,000 test cases, and the deviation from the true parameters is in the order of 10 minus 2. And that is still quite okay, right? And speed of mean reversion, that is instead of 0.13, it's 0.14 or something like that. It's not so bad. It's not so bad. It's quite satisfactory, at least for practical purposes. That is quite good. And for other parameters, the difference, the distance from the true values is even smaller. In CPU, we take 0.85 seconds. In GPU, 0.48 seconds. The total number of function evaluation is still like 200,000, but it goes very fast. And the overall calibration error is of order 10 minus 6. And that was a very satisfactory outcome for us in this practical problem. So I come to my summary. So essentially what we have seen is the problem of financial model calibration. We try to convert it into a machine learning problem. And there the message is we need robust components because we have many different parameter sets and also seemingly parameters that are not realistic. They can come together in a training stage, and still the learning in the learning phase, the classical algorithms should perform. So if we use the cost method, we take a lot of terms. We have a wide interval. It should essentially always converge. We have a network that we call CAN, the calibration neural network. It's robust and generic. It rapidly reaches a global solution, and we use parallelism of the artificial neural network. And essentially, one neural network solves two problems. We have a forward pass for the numerical solution of models, supervised learning, again, very classical, and a backward path for the model calibration and the sensitivity analysis. Always taking into account that we may be dealing with steep gradient functions for which neural networks are just not good, and we need to adapt that. And training, in our case, was highly efficient with our cost method. And that is the end. I have some references here from papers that were inspiration for us. Here is the differential evolution, and the heuristic computing is in an early paper already. Differential evolution is used in neural networks in an even earlier paper. Of course, there are the classical approximation theories for neural networks. And the last paper is also an interesting one, I think. It is a paper from Commerzbank in Germany. And they use this CAN, this calibration neural network, in order to, and they compared it to several alternatives and see if this could be a useful system in practice, in a banking practice. And they considered the can to be favorable. However, there's always a big disadvantage, and machine learning is not yet accepted as such by the regulator. So for that reason, financial industry can only use it for internal purposes, but for reporting purposes, they need to use classical models. Yeah, and with this, I would like to conclude my presentation. I thank you for your attention, and I'd be happy to take any questions.